Let's completely rethink those familiar zigzag lines you always see in chemistry books. Today, we're going on a bit of a visual journey into the fundamental blueprints of reality itself. We're going to decode the invisible architecture of organic chemistry to see how those standard, kind of boring textbook diagrams actually translate into some incredibly deep, highly functional 3D geometry.
There's a central idea that perfectly sets up our whole discussion today. Molecules do not live on paper. They live in 3 dimensions. It sounds simple, right? But to truly understand our physical world, how biology works, and even how the medicines we take actually do their job, we absolutely have to look beyond the flat 2D surface. We need to learn how to visualize the complex architectural space where these molecules actually exist.
Think about looking at a standard street map of New York City. A flat map is great for showing you the basic connections, like where the streets and avenues intersect, but it completely hides the massive skyscrapers, the deep subway tunnels, and the sheer vertical reality of the environment. Well, standard chemical drawings are just like that map. To actually understand how molecules behave and interact, we've got to graduate from the flat street map and learn to see the towering, 3-dimensional city itself.
So here's our blueprint for this explainer. We'll cover the map versus the city, reading the chemical blueprint, adding the 3rd dimension, molecules in motion, the mirror image phenomenon, and wrap up with how shape controls life.
All right, part 1, the map versus the city. Let's get one thing straight right off the bat. Molecular shape is not just some pretty decoration. It fundamentally dictates what a molecule actually does. Get this, 2 molecules can have the exact same chemical formula, the exact same connections, but because they occupy space differently, one might smell like oranges and the other like lemons. Even more critically, the enzymes, those tiny molecular machines keeping you alive right now, they operate strictly by recognizing precise 3D shapes. If the shape is wrong, the machine doesn't work. It literally dictates whether a compound is a lifesaver or a deadly poison.
Moving on to part 2, reading the chemical blueprint.
To understand this blueprint, we have to talk about carbon. Carbon has this unique sp3 tetrahedral geometry that lets it build out in multiple directions, which literally provides the structural framework for all of life. See, the bonds are made of negatively charged electrons, and they naturally repel each other. They want to get as far apart as physically possible. And that specific, highly stable angle, it's exactly 109.5 degrees, pointing toward the corners of a tetrahedron. This specific geometry is what allows carbon to build complex chains, rings, and helices. Without that 109.5-degree angle, life as we know it simply could never exist. Now, since carbon chains can get absolutely massive, think about cholesterol with its 27 carbons, chemists use a brilliantly simple shorthand called line angle notation. To read this, you just need a few basic rules. The endpoints and the corners, those are your carbon atoms. The attached hydrogens are just implied, so they're left invisible to keep things clean. But any heteroatoms, things like oxygen, nitrogen, or chlorine, those must be explicitly written out. It's just a highly efficient visual language once you get the hang of it.
Which brings us to part 3, adding the 3rd dimension.
So how do we show 3D depth on a completely flat screen? Well, chemists use this genius wedge-and-dash system. It's kind of like a 3D movie. A simple straight line means the bond sits perfectly flat in the plane of the page. A solid, darkened wedge represents an object popping right out of the screen toward you, and a dashed wedge means it's fading away into the distance behind the page.
Take methane, for example, good old CH4. With this notation, we can see exactly how it builds a perfect 109.5-degree tetrahedron. We draw 2 standard lines for the flat hydrogens, a solid wedge for the 3rd one popping out toward us, and a dashed wedge for the 4th pointing away. Instantly, a flat piece of paper holds a perfect 3-dimensional pyramid. It's pretty amazing.
All right, part 4, molecules in motion.
Here's where it gets really cool. These 3D shapes aren't just frozen statues. Single chemical bonds rotate freely, acting like 2 propellers spinning on a central shaft. Because of this continuous, endless rotation, molecules are constantly dancing and shifting between different spatial arrangements at room temperature. In chemistry, we call these distinct shifting poses conformations. You see, nature always prefers the path of least resistance. It highly favors what we call a staggered conformation. In this staggered pose, the atoms are maximally separated. Everyone has plenty of personal space, making it a very relaxed and stable state. But as the bond rotates, the atoms eventually align and directly overlap in an eclipsed state. This causes high energy and a lot of spatial strain. Naturally, the molecule wants to spend as much time as possible back in that relaxed, staggered state.
This exact preference for comfortable angles is why a 6-carbon ring, like cyclohexane, flat out refuses to sit like a flat hexagon. A perfectly flat ring creates terrible structural strain, so instead it puckers up into a 3D chair shape, perfectly preserving those ideal 109.5-degree angles. Now, in this chair setup, atoms pointing straight up and down are in very crowded axial positions. Meanwhile, atoms pointing outward along the equator are in equatorial positions. Any bulky groups attached to the ring will naturally shift into those spacious equatorial spots just to avoid bumping into their neighbors.
When we pull all of this together, it is just an incredible, elegant system. You go from the basic flat framework to understanding carbon's 3D tetrahedral geometry, applying the wedge-and-dash notation, and finally seeing cyclohexane's shifting chair conformation. It all maps out the precise, architectural language we use to navigate the microscopic world.
Now for part 5, the mirror image phenomena.
Okay, if you ever spot a carbon atom bonded to 4 entirely distinct groups, like, say, a hydrogen, a chlorine, a fluorine, and a bromine, you have found yourself a stereocenter, sometimes called a chiral center. And honestly, when a carbon has 4 completely unique attachments, things are about to get weird.
These stereocenters create something called enantiomers. Basically, they are exact mirror image molecules that cannot perfectly overlap. Think about your hands. Your left and right hands are mirror images, but if you try to lay them flat over each other, facing the exact same way, your thumbs point in opposite directions, right? Molecules do the exact same thing in 3D space. They create distinct left-handed and right-handed versions of the exact same chemical formula.
And finally, part 6, how shape controls life. This is where all this abstract geometry transitions directly into life or death biology. The molecular machines inside you are incredibly picky locks, and they will only accept one specific 3D key. For instance, your body runs entirely on right-handed D-glucose. It fits perfectly into your metabolic enzymes. But if you were to eat the mirror image, L-glucose, it would pass through your body completely unrecognized. Biology plays absolute strict favorites when it comes to geometry.
Whether we're talking about the strict, right-handed spiral of your DNA or the history of pharmacology, these microscopic spatial differences yield massive real-world outcomes. A heartbreaking example of this is the drug thalidomide back in the 1950s. One mirror image of the molecule effectively treated morning sickness in pregnant women, but the other mirror image enantiomer, the exact same atoms just arranged left-handed, caused severe birth defects. The lock and key mechanism of our bodies is so precise that a single bond pointing away from you instead of toward you changes absolutely everything.
So, to an organic chemist, every single zigzag is a carbon, every solid wedge is depth, and every dash is distance. Chemistry truly is the study of precise spatial arrangements. As the source material beautifully puts it, organic chemistry is not the study of lines, it is the study of invisible architecture.
You aren't just looking at random lines on a page anymore. You are literally seeing the framework of reality. From the medicine sitting in your bathroom cabinet to the DNA spiraling inside every cell of your body, shape fundamentally dictates existence. So now that you know how to read the true 3-dimensional blueprint of the universe, how will you look at the world differently?